Hi, my name is Oliver Schön, and today I want to talk about correct by design control for parametric stochastic systems. The agenda is quite straightforward. In the first part, we're going to talk about correct by design control for the standard case of non-parametric stochastic systems with the kinds of problems and an abstraction-based solution. And then in the second part, we're going to go over to the parametric case, giving our notion of subsimulation relations, some numerical results and extensions. So what is correct by design control and why is it interesting to look at this? For our case, we're going to look at systems, in particular safety critical systems, that evolve in uncertain environments, which means that the state evolution of the system is subject to uncertainty. Where the goal is now to design a controller such that this system, so the control system, exhibits some desired behavior. And for this talk, I'm going to use an illustrative example of an autonomous car. And the desired behavior shall here be that I want to avoid some obstacle region A, go to an overtaking lane B, and eventually reach some target set C. Now this can be concisely specified using a language such as SCLTL, and that's exactly what I said before. I want to avoid region A until reaching C, and once reaching B, I want to eventually reach C. Note that the eventually and implication operator here are derived recursively from the basic semantics below. Now the task is to design a controller such that the control system exhibits this specified desired behavior with a probability of at least, say, 99%. Recall that since we're having a stochastic system, there is no binary notion of satisfaction, but we're looking at probabilities of satisfaction. Classical controller theory cannot provide any solutions to these kinds of problems, and one kind of solution for this is robust dynamic programming that was introduced in 2020. And for robust dynamic programming, what we have is that we're looking at the true system dynamics, which in this case with a system state X and a control input U, as well as some stochastic noise W. However, these true system dynamics are usually not known, and that's why it's desirable to be able to tackle this anyways. And one approach to this is to specify a parameterized model. So we reformalize that whole thing into a model where the parameters are unknown. For example, in our car case, the mass of the car could be unknown. And what we now did is we reformulated the problem over unknown system dynamics into a problem of parametric uncertainty. And one way of tackling this kind of problem is that we utilize data-driven system identification to take data and then learn a confidence set which contains the true parameters with some given confidence. And this is also what we do in this paper. However, for the first part of the presentation, I want to look at the state of the art before, so where the true system dynamics are given, and then in the second part I'm going to go over to the parametric case. Now, we have the true model, and at every time step k, the controller observes the state of the system and gives us back a control input. This control input then takes our model from state xk to a consecutive state xk plus 1. Recall that we have a stochastic system, and hence our consecutive state is also defined by some probability density function. For modeling this, we use a transition kernel T, which is basically just assigning probabilities to every instantiation of the consecutive state, given some prior state and control input. The objective in mathematical terms is now to design a controller such that the probability of satisfaction for the control system is lower bounded by, say, 99%. The problem is that for stochastic systems, these kinds of objectives there exists no closed form solution for these kinds of problems. And hence, one solution approach would be, for example, using an abstraction-based solution. This is very similar to model-based approaches, where we now have a finite state abstraction of our model. What does this mean? If you look at the plot on the left, we are gridding our state space, and from a continuous probability distribution, we now obtain a finite state one, discrete one. This can now be solved using the robust version of dynamic programming, which will also give us robust satisfaction probabilities for the abstract model. However, if we implement this in the real-life system, what we want is not guarantees on the abstract model, but guarantees on the true model. And this is where the concept of simulation relations comes in. This is a very established concept which allows us to pass on the guarantees that we get for the abstract model to the true model. The only thing that we need to know for this talk is that this is quantified by some parameters delta and epsilon. And it's basically just saying how similar are the two models evolving. And what this allows us to do is that if we have the simulation relation, then the probability of satisfaction for our true model is lower bounded by the satisfaction probability for our abstract model, which we know. And this comes in very handy as the central approach of this kind of procedure. So now that we know how to solve the non-parametric case, I want to come back to the parametric case. Recall that what we did was we just introduced some parameterization, and these parameters are generally not known. So for example, for our car, we would have the mass of the car being 1 ton, and you get some transition probabilities. And for a slightly different parameterization, you get a different one. And since we have some data from the system, we can construct this confidence set. And if we take all the models for all possible parameterizations in this confidence set, we also obtain a set of models. So what we want to do is have this kind of setup, where we now have not one model, but a whole set of models. To get the guarantees on this set of models, we also want a simulation relation which works not between two singular models, but between one model and a whole set of models. And this doesn't exist yet, and this is our main contribution, which we call subsimulation relations. Similar as before, this now allows us to do that for all thetas in our confidence set, we're going to have the same kind of lower bound on the satisfaction probability. Maybe also to put this into context with prior works allows us to construct a controller which is also parameterized on the unknown parameter. However, if we now embed this into a system, at runtime we also have to know these parameters, and we only get the guarantees for this specific choice of parameters. So this is not going to help us, because what we want a universal controller which works for the whole confidence set, because we don't know the true parameterization. So for the sake of this presentation, I'm going to show only a very brief overview or insight in how such SSRs, subsimulation relations, are constructed. And in particular, I want to show the difference between prior definitions and this one. And this is going to be the only slide where there's going to be some more complicated maths. Bear with me. So this is the same setup as we had before. We have a controller which gives us a control input for our abstract model. This is mapped to a control input for our true model. And the true model then, with some parameterized transition kernel, would give us back some state. Using a state mapping, this is then mapped back to the abstract state space, and the circuit is closed. For subprobability couplings, or for subsimulation relations, or in the general case normal simulation relations, what we always do is we look at the so-called composed transition kernel. So one model, M hat, is evolving according to some transition kernel, and the other models also to some different transition kernels. If we now look at the product space between the two, we can look at how these two systems are evolving in parallel. And what we usually want to do is that we define some relation between the two and then integrate over this, giving us some probabilities that these models are going to behave in this manner. And this is exactly the same that we do for SSRs as well. So we take our state mapping and multiply this with our transition probability. This is going to give us then the composed transition kernels, which is exactly saying, oh, this is how the two systems are evolving in parallel. For prior works, we would now show some properties of this composed transition kernel. However, if you look at this, we still have the influence of our unknown parameters. And that's what we do. We want to find some subprobability measure that lower bounds this composed transition kernel for all possible theta. And we can then show these properties for this subprobability coupling. Maybe to make this more clear, I want to use this kind of picture that we have for our abstract model, we have one transition kernel. And for unknown system, we have multiple ones and here, for example, just plotted for two different parameterizations, but in general, a whole bunch of different probability density functions. One possible subprobability coupling in this case would then be just the intersection, and we can then show some properties of this. The interesting part here, and the main thing why I'm talking about, is that for the non-parametric case, the area under this curve would sum up to 1. However, if we integrate this subprobability coupling, this is not going to be the case. And this is exactly why accounting for parametric uncertainty is going to introduce some kind of conservatism as well. Obviously, if we recover the complete probability coupling for non-parametric cases, or if the confidence set shrinks to 1 point. Now, how does this all fit together? For the procedure that we're describing in our paper, we're looking at 3 layers of models, where here I indicate the level of abstraction. So we're starting with a set of feasible true models, which contains our true model with some given confidence. Then we choose one nominal model of this, for example, just using the estimate of our parameters. We then grid this model, so we have a discrete abstraction for it. And what we can then do is that we instantiate 2 simulation relations, because we have 3 models. So the first one is our new SSR, and the second one is as before. Using transitivity properties, this is the same as having one simulation relation between the first and the last model. For the discrete abstraction, we can then use prior works to synthesize a robust controller, which gives us guarantees on M tilde. And leveraging our simulation relation, we then also get robust satisfaction probability for the set of models, and implicated by that also the true system with some confidence. Now I want to use this opportunity as well to make everyone aware of SySCoRe, which is a MATLAB toolbox that we've been developing, which is basically implementing and automating all the steps in synthesizing a robust controller that I've been talking about in this talk. And it takes as an input the model of the system and specification, and then outputs a robust policy as well as bounds on its satisfaction probability. And the kind of features that we can handle are nonlinear stochastic dynamics, arbitrary support, possibly infinite horizons, unbounded specifications, model reduction, and we also exploit fast computations. The tool paper is accepted to HSCC, look out for that. And there we also competed in a friendly competition called ARCH to show our performance. If you're interested in that, feel free to look at that as well. Because I also want to leave some room for numerical results. In the paper itself, we're looking at one linear and one nonlinear system with Gaussian support, and we compute the lower bound on the satisfaction probability. Here I'm just going to talk about the linear case, where we're basically just looking at a car which is traversing in a 2D plane, and we want to avoid some obstacle region P2 and park in parking lot P1. The lower bound and the satisfaction probability here that we get is quite straightforward. Obviously, if we start in the parking lot itself, the satisfaction probability is going to be 1, and the further we get away, the lower the satisfaction probability is going to go. To summarize, our main approach here again is that we estimate the confidence set theta from data, and with some confidence this is going to contain our true parameterization. We then express the parametric uncertainty in our model as a feasible set of models. Our new sub-simulation relations then allow us to construct a simulation relation between a single model and a whole set of models. And this is how we are able to address the system model mismatch. So what are future direction for this? In this paper, we're assuming that the confidence set is given, and next we want to estimate this robustly from data. And to motivate this, if we look at the picture on the right and we decrease our confidence set to a third, the satisfaction probability is boosted by a lot, which means that the conservatism that is introduced by our approach is also reduced to a minimum. Therefore, in our extension, data-driven correct by design control for parametric stochastic systems, we're going to utilize data-driven parameter estimation to get less conservative results. Look out for this. So this brings me to the end of today's video, and I want to thank you for your attention. And I also want to thank my collaborators. Feel free to get in touch with me for any comments or questions.